Okay, let's wait one more minute. Okay, good afternoon, everyone. My name is Francesco Petruccione, and I'm at the moment the interim director of NITheP. And this afternoon, I have the pleasure to introduce to you Professor Nico Orce. Nico is based at the University of the Western Cape, and I think by training and he's a nuclear physicist, and he's worked at all the major nuclear physics facilities worldwide. Yeah, but today he will speak about something completely different that is probably close to all of us in this particular moment in time, which is the COVID-19 situation in South Africa and possibly in the rest of the world. And he will discuss it using some stochastic simulation models that might find use as well in nuclear physics. Yeah. And with us on the panel is also Professor Ilya Sinaisky, who will kindly moderate the questions at the end of the talk. Yeah. And Nico, people are not here to listen to me, they're here to listen to you. So if you would like to start sharing
I can share the screen now, right?
Yes, please.
So
and maybe while you share the screen, the usual recommendation to the attendees to please use the Q&A facility to ask questions, and we will give Nico later the opportunity to answer them. So Nico, thank you very much.
Thank you so much, Francesco, for the invitation. I'm very proud to have become an associate member of NITheP recently. And today, like almost every day, we have been monitoring what the situation since the beginning in Wuhan. We have been monitoring the situation of COVID-19. So we have learned quite a lot with time. And hopefully we can come with some interesting conclusions today. So we have monitored worldwide the spread from COVID-19. And as every day, the minister, Mkhize, around 9 o'clock, between 9 and 11 p.m., he brings up the new statistics in South Africa. And this is what we see every day. And we try to make sense of the data that comes to us. Then it goes to worldometers, it goes to the different databases in the world. But the first place is 9, 10, 11, Twitter. Dr. Mkhize sends the latest information of what's happening in South Africa. And you can see the data here for the different provinces, the total number of deaths. As from yesterday, we are reaching 48,000 total number of deaths. And so we actually reach a low in the daily death, 78. If we do the average, I will show you later. And here sometimes the recovery rate, which is basically the ratio between total recoveries and the positive cases identified. And the latest news, I don't know if it was probably online, I don't know where, but I found it that someone in one of the WhatsApp groups sent me the information that level 3 lockdown has been extended until March 15, with the addition that we are reopening the land ports with neighboring countries, and still beaches are open, and other things that were other measures that were lifted or were released last February the 2nd. So it's been 12 days since we are still under the original level 3 conditions. Remember that it takes a while for, once you change the lockdown conditions, it takes a while for people to start getting, to die. There's a time of death which is about 20 days, 25 days, 15 days, depending on the situation, the case. And this is what we see. We are going to be focusing on death cases, because we think it's more reliable, because infected cases, they depend on the test, different kind of tests everywhere. So, but also we look at the infected cases if we need to. So let's continue here, and let's introduce the main players of this story, which is one of them is Jose Enrique Amaro it was my quantum mechanics teacher. He used to spend 6 months at MIT, and he has written books on how to program with your Android machine, Android cell phone, and he has been very much involved also in the predictions for South Africa. And this is his webpage. You can go to his webpage at www.ugruniversitydofgranada.es, Spain, _Amaro, and you can download the pandemic application for your Android here. This is a very cute thing because actually, if you I have it here somewhere, but if you can actually go and you can change the parameters. This Monte-Carlo simulation that we have developed is based on the Planck model of photons in statistical physics, and it has a temperature, energy. So you will understand quickly what the parameters are all about. But this has been done in a user-friendly way, so kids at schools and anyone can actually play with the parameters, with the depth interaction with the depth, average depth numbers. You can play with all these numbers and these parameters that they are involved in the Monte-Carlo simulation, and try to stop the pandemic, right? So this is a very interesting tool. You can also watch the movie here. Maybe we could actually, but I will show you just quickly. Let me see, what is my internet connection? Here. So I think I have it somewhere. I have here, I think. Coronavirus. Well, I don't know what is the Amaro. I have it open here before, but basically, let me see, just Amaro and coronavirus. Here you can see. Here we go. You just Google this and go to the pandemic application. You just download it, and basically it works like you will see the spread of the pandemic depending on the different parameters. You can play with them, and we'll mention a little bit on the parameters a little bit later. So then another player, I don't want to, because the movie will take some time, and you can always go there. Another big player is Jeremy Dudois. He actually is one of those computer geniuses who works at the University of Lyon, but he's very much involved in any nuclear physics campaign at the big laboratory in France, Ganil. And he does all these computer-friendly codes for the users to arrive to France and see that the data is coming, and look at the different visualizations of data and particle gamma coincidences. He's really good with root and C++, and not only root but C++, also Python. And he does a lot of visualization, as I say. And these beautiful plots that we see here with the different error bands, they were developed by him in practice. And you can see, actually, these are new ones that you probably haven't seen anywhere. This is the United Kingdom for the second wave. This is the second wave for Italy. Different models that I will explain a little bit later. For Sweden and for Switzerland, it just shows a few of them, just to show the kind of plots that Jeremy has nicely developed. Also, he has a user-friendly program. You can just go there. It's even simpler than using root and C++. But for our students, I prefer that they learn the C++ a little bit. So we have been, as I said at the beginning, we have been monitoring the pandemic evolution, and we have shared this in social media, in Facebook, in LinkedIn, in Twitter. So everyone participated at the beginning of the pandemic, and we have improved altogether different codes, the different understanding of the phases of. I will have been explaining, for instance, in the media that the inflection point of the D model curve is given by B natural log of C. I will explain these parameters in a bit. But all the information about the models have been distributed regularly with everyone. So and this, it was quite a thing to follow at the beginning, and even now you have people like 1,000 views per post. So we have important contributions from friends, Facebook friends, and also someone who were not so good friends, but we also accept any criticism. At the beginning there was a lot of criticism, but things it's always good to get criticism, because if you don't get criticism, that means that you're doing nothing. Or what do they say? Do nothing, say nothing, and be nothing, right? So it's good to have to discuss in a nice way what the weakness of the models are, because they're always weaknesses. These models are not perfect, and in fact we try to make them as simple as possible to avoid any, I don't really like, as I will mention later, these many parameters and models, because as in nuclear physics, we have nuclear interactions, but we don't really know the nuclear force, the nuclear force. We have models, or realistic interactions, they call them, with more than 30 parameters, and this is what we have as a nuclear potential, unfortunately. So we have also created YouTube videos, and you can go to my YouTube page, Nico Orce, and you can have there are videos on the D model, different seminars that we have given, and it's very interesting to see the progress from day one, from some of the calculations that we originally did. These calculations have been given, some of these videos were given to, well, actually requested by the University of Pretoria, by Chris Theron. So I made one video for them, and we did some computational pracs for the second year students there. Actually, Chris Theron did most of it. I just introduced the model, and the students were very happy with trying to simulate, trying to do some modeling of COVID-19, which is very interesting nowadays. And this is actually is a very grim subject, but as I will show you, can be used, and this is our purpose, can be used in a positive way, because there's a lot of concentration from everyone on COVID-19. So it's a good time for transformation. It's a good opportunity for us to use this grim subject and convert it into something more productive and interesting, actually. So finally, all this work for many months. So it was published in Applied Mathematical Modeling, and you can find detailed information of the paper. It's quite a long paper there, and it was entitled Global Analysis of the COVID-19 Pandemic Using Simple Epidemiological Models. And the main highlights were, like, we solved the ESIR transmission dynamic equations analytically, with and without recovery assumptions. At the beginning, it must be said that the D model, the DETH model, doesn't have any recoveries. So we assume that there's no recovery, and this was criticized badly, which fair enough. Our models can characterize the evolution of a pandemic at its different stages, exponential, and what here I call normal is more like a slowdown phase after the exponential phase. Our models can be extended to describe additional spatial-time effects, like those from the release of lockdown measures, different migration. Migrations is not considered in our models, because a priori we have a closed system, as we shall mention in a little bit. And similar results. We'll see this later from a model which shows, which provides the possibility for recovery, and the D model which has no recovery into it, suggests that most acceptable become infected, asymptomatic, and eventually recover. This at the beginning was at that time was a very strong message, but we see today that this wasn't so crazy as we claimed a while ago. Although it says here that this is February 2021. It's like a brand new paper. Actually, this was published already, I think, in September last year. So similar trends suggest a common pandemic evolution with universal parameters, and we'll see this as well. And this eventually became an Elsevier public health emergency collection. Remember that this applied mathematical modeling has an impact factor of almost 4, which is rare in any mathematical journal. Have an impact factor of 4 is quite a strange or difficult thing to have in mathematics. And all of these models and all these applications, Python, C++, through Root is the program, data analysis program that they use at CERN. So for all of those who are in physics, many of you will be able to will need to use Root at some point and learn some C++. But also we have Python, Fortran, Java for the Android, Monte-Carlo simulations through the Fortran code that we have. And this we like to introduce it into this workshop that we're having, this mini school in March. So for that, we will require 2 conditions if you want to be able to run these codes. You will need just a Linux operating system. You can take a USB, and even if you have Windows, you can plug it in and run Linux during that time. Obviously, you will need to install G, Fortran, and all the Python libraries and everything. And we have the participation of the authors of this paper, including Aswandini Muronga, which and Daf Matebula, who is a mathematician at the University of Venda, and other people. We may have other postdoc of ours, people who may contribute to help, during the mini sessions that we'll have. We'll divide the students in different sessions and see what they come with. So now let's go to the actual model, and this is the DETH model, the extended CERN model. Everything is based on the old ESIR model of susceptible, infected, and recover, although it's not so much of recover as removal. Actually remove, I will say, because in recover we have both. You can recover or you can die. So this is the typical approximation. It's a good approximation for viral diseases, how they spread, because unlike bacteria sometimes you can go back and get infected again with the same bacteria, but with the viral diseases, normally is the case that you cannot go back. So you go from susceptible to infectious, and then to remove, say, instead of recover. But you can never go back from recover to infectious and to susceptible. So basically, it's a one-way spread, and this is characterized by a transmission dynamic system composed of 4 equations, where we have a fixed population n, where n, as I write down here, is given by the total number of susceptible, infected, and removal, or let's call them remove cases. So as you can see, if you open the lockdown restrictions, then obviously lifting lockdown restriction leads to a increase of n. The infected population can increase because people can move from place to place and infect other people. So these equations, obviously, they are valid among the conditions that we have a fixed population. That population doesn't change. What is the amount of that population? is difficult to know. So it can be a whole country, it can be a city, it can be a region. I will see this. We'll see more about this later. So obviously this equation, the susceptible rate, you have a minus lambda, which is the transmission rate or the spreading rate, and then multiplied by susceptible and infected. The infected rate is also the probability of infected minus the possibility of recovery. And the recovery is obviously proportional to the recovery rate times the infected. And the total fixed population or closed population N is equal to the sum of the three. Right. So this is based on the 1927 paper by Kermack and McKendrick, and there was a breakthrough at that time. So obviously this means also that if we can only go one way, so the only way not to get more susceptible into the picture is by isolating everyone, right? Or by applying the preventive measures of washing your hands, typical keeping distance, wearing masks, everything that we know so well, and that people must obey at all times if we want to kill the different waves, particularly this one. Without vaccination, the only way to reduce the transmission or infection rate is by implementing these measures. As you can see, the vaccination rates per 100 is very good in the States right now, in the UK, in the Arab Emirates here, in Israel, and in some European countries, but in Chile. But in Africa, it doesn't look like we are going to have herd immunity very soon, hopefully. I don't know what is the plan for the government, but so far this was for February 13th, so we don't have much of vaccination done already. So this is another web page which I recommend to go and check what is happening, our world in data, to see how far we are with vaccination. So then the death model that we introduced from the ESIR equations is a simplified version of the ESIR model under the condition of no recovery, as I mentioned before. So basically you have RT is equal to 0 and lambda is greater than B, right? So if we do so, actually we can go quickly check here. Actually, yeah, I have the equations here. So basically by assuming lambda greater than B, we can remove this term here. We can assume there's no recovery. So this goes to 0. This term is negligible. This term is much smaller than this, can be taken away, and everything reduced to one order differential equation, first order differential equation, which is this one here. You can then you can divide by n minus I and multiply by dt, and you get this equation here, which is easy to solve by multiplying both terms by n. This term becomes this, and then you have n lambda t, and basically it's easy to solve this differential equation, which leads to a function like this for the infected rates, infected cases as a function of time, and by using a change of variable, this is the death as the death functions as a function of time, we reach what we call the death model equation, which is given by this formula here. So basically, it's very easy, but just by assuming in the system of SIR equations that lambda is greater than beta. So beta, we assume beta is negligible. We remove the beta term from here, and we remove r from here. So susceptible will be n minus I. So we just n minus I here, and this will be the equation that we have to solve. So it's very simple, very easy. From 4 equations, we reach to 1, and this leads to the death function right here. And let's go back to the presentation. Basically, assuming that the lambda, the transmission rate, is much greater than the recovery or removal rate, we reach to this infected function that we can use and we want to use later. And by doing this change of variable, we can go to the to the depth function, which is given by a exponential t over here. We have a, b, and c, and this tau here is the typical death time plus minus 25 days, and mu is the death rate. So if we look into the parameters, all parameters are embedded into this in the parameters a, b, and c, which represent space-time averages and can be fitted to the timely available data, right? So this function here, we just take the data and we can see how our function goes and how we can predict the trend. So there are different possibilities, and we can discuss about the different parameters, but this is what is happening typically before we reach the peak. No one knows what's going to happen. No one knows when essentially it's very difficult to predict when the peak will come unless we are almost there at the peak. So at that time, the system is wild. It's complicated. We have done it in a few lucky cases, but generally the situation needs some stability, which is reached probably as we reach here. This is just number of days. This was some of the data we took from Spain at the beginning. And there's sometimes where the parameters are stable, but suddenly, you see a sudden rise of on the parameters, and probably this is because something changed or there was a new population coming up. So basically, you have a parameter which tells you what is the number of deaths at time 0. So many times, we say that there's only one death in Spain on the something of February, but then the death model actually show, which we will see in a little bit, that A is probably 20 or 30. So that means that when the government says there's one death, the D model predicts that there were actually 30 or whatever is the number for the A parameter. B is a typical characteristic evolution time of the exponential. So it tells us in how many days the number of death cases will double. But also it tells us the width of the D prime function, the full half width maximum. It tells us something about the inflection point, and A over C, as you can see, you apply L'Hopital here, and you do the derivative of the numerator and the denominator. You have at T infinity, you have that this is equal A over C, which gives you the total number of death, A over C here, right? So you can see it increases with time until you reach some time of stability, and then you have the flattening here, about 16,000 cases, which was about right in Spain. Spain was 20 few thousand, I think, the number of deaths at that. So C is the inverse death factor, and also it plays a role. The interplay between this exponential and this exponential is crucial to see, and we'll see in a little bit when the exponential phase ends. So you can learn from the paper what these parameters, what they account for. It's very interesting to have a look at them and see, when you look at a function, everything, all these parameters account for something, because this is not just a function. They are coming from solving the ESIR equations, right? So this is not just a parameter, but they all depend on a particular recovery rate, on the total number of the population, on the infection rate, on tau here, the death, the number of the typical time for dying after getting infected. And we always think about parameters because we don't want to, as I mentioned at the beginning, I don't like things when they become with too many parameters. And so we have done different models, and we call it whenever we have a new wave or a resurrection of the old wave, resurgence of the old wave, we always we can have a possibility to add two D functions, right? And then that will explain better the situation. Although we try to use what we call the reduce, and we mentioned this later, reduce the D and ESIR2 models with reduced number of parameters. But I always keep in mind, I always tell my students that this story of Enrico Fermi and Freeman-Dyson. So Freeman-Dyson, probably you know the story. Freeman-Dyson went to visit Enrico Fermi. He was very proud of his new nucleon-nucleon interaction. As I mentioned before, these nucleon-nucleon interactions are a little bit complicated. They have been complicated for many years. And still we don't know the nucleon-nucleon interaction. And Freeman-Dyson went to Enrico Fermi, and Enrico Fermi was looking at him and he said, look, it's a nice one, but how many arbitrary parameters do you use for your calculations? And Freeman-Dyson thought for a moment about the cutoff procedures and said 4. Well, Enrico Fermi, I remember my friend Johnny von Neumann used to say, with 4 parameters I can fit an elephant, and with 5 I can make him wiggle his trunk. With that, the conversation was over. I escaped to Berkeley. They published a paper on this because he couldn't let his postdocs down, to start a new career in condensed matter physics. So this is, he always is very, very glad, very happy that Enrico Fermi told him the truth, what he thought about his model, about, you know, having too many parameters involved. And this is part of the game, but we try to reduce it as much as we can. So then we applied our model first to China, obviously. It was the first case. And it worked very nicely, actually. The data follow the trends in China. So it was a good encouragement to apply it further. And you see here is this is the accumulative deaths, and here we can see the deaths per day. So obviously this is this has more data fluctuations than the accumulative deaths, right? So we always go for this kind of plot rather than this one. This is more certain than this one because this presents more fluctuations. So this analytical solution involves framing the problem in the well understood form and calculating the exact solution, which allows the D model fit to data and explore pandemic evolution as new data coming. Obviously, the more data you have, the better, as these are statistical models, right? So then here came one, I think, a little breakthrough of the D model, because there was some arguments about whether we were on the exponential phase or we were on the what we call here the slow motion phase, right? So the exponential phase is something very scary. You know, you plot the data and you see this exponential phase. This goes to hundreds of thousands of people dying, right? This red curve goes all the way up and it stops very far away. You know, it's a very scary thing to fit. So I always cut it here. I always cut it somewhere where you cannot see so many dead people. But the fact of the matter is that the situation changed. This is a fit to the data in South Africa for the first wave on the 29th of May. And this was a fit done a little bit later on the 13th of June. And already before the 13th of June, we could see that there was a little deviation from the data points, you know, from the exponential phase to the, what I say, the slowdown phase, right? The phase that leads to this flattening of the curve, they call it, right? The plateau, which gives you the total number of deaths, right? So as we saw in the parameters, this will increase a little bit as time comes. But it was clear from this moment, early June, that we were out of the exponential phase, you know, and this was something to prove later, obviously, because we were not 100% sure that, because everything looks very exponential at that time. But we realized that through experience that the D model was very sensitive to deviations from this exponential phase, and we could predict the end of the exponential phase quite reliable, right? And this all depends on the parameters A and C, how they change, right? The interplay between the numerator and the denominator in the D function, and the same thing, you know, once you do the derivative of the D function, you get the D prime function here, and you could see there was a peak finally. Otherwise, this will go all the way up as well, and you could see that there's a there's a coming down after the prediction already of the peak on the 15th of July. So this, again, this is the peak coming from the daily rates. But as you can see here, the D model, well, this is just an explanation of what I was trying to say before. The D prime model predicted the 15th of July, but this has large statistical fluctuations, in the daily rates. They change quite dramatically. Even when we try to use a 3-day data, 5-day average or 7-day average, obviously at the end we went for the 7-day average, which provides less fluctuations. And this was at the beginning of times. So most of our plots, they use 7-day average data nowadays. So and as I say, remember that this is the effect, the deaths per day, and the cumulative deaths is the effect of having those infected about 20 days ago, 20 plus minus 5. It's not really clear what is this the death time. It can be 20, sometimes can be 15, so can be 25. Depends on the well. There's an uncertainty there, but it's easy to deduce because you just have to wait. You wait level 3 restrictions, right? You wait and say, okay, so we have level 3 restrictions. The 2nd of February, we open the beaches, and my kids, the school open last week already. Some schools open last week, some schools are open this week, some schools are open next week. No, actually this week. So this will also play a role. So I think from level 3, 2nd of February, once people is allowed to go to the beaches, although we are still in level 3, we are going to see a difference. Obviously, the difference will increase if we have the schools opening. So eventually, we can determine more or less what is the time for people dying after getting infected. But then, obviously, with the cumulative data and with the D function, you can also get I don't write it down here, but this is the inflection point, which is the time of inflection. Here is actually is B, parameter B, times the natural log of t. So by using B natural log of t, you can know what is the inflection point, which doesn't correspond always to the peak here, because what I said before, this the cumulative data has less statistical fluctuations, and we prefer to look at the D function. And there was a little bit of a shift between 21 of July for the peak compared to the 15th of July given by the daily rates. But it was more precise, the 21st of July, which is basically B here times the natural log of C, right? So that gives you, I think it was like 100 and few days from day 1, which was the first death, which happened the 26th of March. So again, as I mentioned before, not additional effects like, for example, special migration from N2 townships to the Eastern Cape, or level 3 June 1st. There was another level 3 in June 1st. So these things are going to be considered, probably considered by another D function. So limitations of these predictions are obviously we need data. The more time and data that we have, the smaller will be these error bands, error propagation that we have here. As you can see here for the United Kingdom, very precisely, very unprecisely on the 29th of March. You don't know what is happening. You predict even a second wave here. But if you move a little bit later, almost like a month later, the situation is much better. You move, obviously, another month later, the situation is even much better, and so on and so forth. I mean, obviously, this is for the D model. The extended CERN model is going to give us a better prediction, but we shall see that later. But you can see the error bands, how they narrow down as time comes and more data comes in. So this is another very interesting point that we normally don't make, but we see that for a total population in Spain, this also applies to South Africa, to any country, a total population of 1 million. Eventually, as we go with time, most of the population or the whole population get infected, right? And there's a difference on how you go up, depending on this tau, which I mentioned before, is the typical death time for if you get if you're going to die from the time you get infected to the moment you die is 15 days, 20 days. Obviously, if it's 20 days, you're going to go up faster than if you have a short time of death. And but still you're going to have a percentage that you can see here better of death versus infected, which is about 2%, 1.6, 2%, which is typical of the actual situation that happens in most of the countries. So most of the people get infected, a total population, everyone get infected. This comes from the D model, right? And about 2% of those infected cases die. Here, again, you can see the same situation, infected versus the total number of population, 1 million. And again, you can see how if you got 20 days, you reach the plateau earlier than if you have a shorter death time of 15 days, right? So again, the important result here is that most people get infected. So we have a very contagious disease. But most people, as we shall see, most people get so in the D model, there's no recovery, right? So if there's no recovery, what are these people? They get infected and that's it. They keep infected all the time. So the D model suggests that they are infected, or these are the people who are mostly asymptomatic, right? So most people become asymptomatic according to the D model. And this is something very curious because this has been argued before experimentally, and it was by the University College London, where they found that they calculated, or from data, that about 86% of the UK COVID-19 patients have no symptoms. So, and this was kind of strange. Or most people become asymptomatic, and in this case, all the COVID-19 patients, but not only the COVID-19 patients. It seems to, because recently, last Friday, actually, already a new study in South Africa, led by the National Blood Service, shows that a large percentage of the South African population had probably already been infected with COVID-19, right? Up to 63%. So the D model predicts that most of susceptible population and get infected, and as they don't die, they have to become asymptomatic, right? So again, COVID-19 is extremely contagious. And now we go to the next. The next point was the extended SIR model, right? We had to test all these ideas of asymptomatic, but we didn't know what happened with all this population. What happened with these guys? Are just infected all the time and that's it. So we needed to solve the ESIR equations, assuming that there's a recovery. And for that, we went through the typical, this is the general ESIR equation that you can find in the books and in the papers, that 1923 paper. And this is the normalized ESIR equation, which can be solved in particular case, assuming, for instance, that this exponent here is quite small, which is not real at large pandemic times, at the end of the pandemic. So there's some limitations in this solution. But we assume that we propose here at this stage, we propose something new. And we propose a parameterized solution with the functional form of the D model, this one here. And basically, assuming that the death function is proportional to the recovery rate here, this is basically characterizing what we call the ESIR model, the extended SIR model, right? Which includes recovery, but another additional condition must be added, a time condition. A boundary condition, obviously, that if there's no boundary condition, there's no solution for the extended SIR model. However, if you add a boundary condition, in this case of this is the D prime function here, the change in D, this is basically the extended SIR model. If you apply a boundary condition for the time of the at 100 days after the pandemic started, let's say that there's a final number of deaths of 10. So we also change to 5. And if you just numerically, you just allow for a few deaths at the end, like after 100 days, you have 5 deaths, right? So then obviously the curve comes down, and you can have a similar curve which you can feed to data. And you can see there's not much of difference between these two plots by changing the number by 10 to 5. So the use of no boundary condition, as I mentioned before, is not an exact solution of the ESIR differential equations or differential equation. A way to solve this problem is to impose a condition at d prime infinity is equal to 0, but numerically is enough to add some number, 10 or 5. So basically, you need to fix the extended SIR model at some further time to make the plot come down, right? The curve to come down when you do the fit. Otherwise, the fit will continue forever, right? The curve will continue forever and will never come down. So in this case, in the SIR model, as mentioned before here, this equation, this was the function that we parameterized. And we have it here as well. And again, as a large T, this is 0, and then the total recovery rate is A over C. And we look at A over C here, A over C, 0.0002121, 0.0002126. So they are very similar to 1, right? So for the extended SIR model, as time goes to large time, in this case 100 days, for instance, the recovery rate, the recovery basically goes to 100%, right? And this was another very important situation, which reminds us of what happened with the D model. And this gave us consistent results in terms that all those people who are actually infected in the D model, they eventually recover. They must recover because the extended SIR model says so. So the only conclusion is that those infected actually became asymptomatic and eventually recover, right? So this is the conclusion from looking at the two models, the death model with no recovery and the extended SIR model with recovery, right? So this is the D model here on the left, and this is the extended SIR model here on the right. So this was, I think, quite an important result by combining the model predictions from the D and the extended SIR model. Obviously, also we can do instead like we have done with the D model. We can have two D functions. We can also have two extended SIR functions, and this is what we did here. And we can have the extended SIR 2 equation given by a similar equation, but in this case, RT is given by two functions, which by experience we realized, not only by experience but also by conditions, that R at infinity is equal to 1. We can assume that A and A is equal to A prime and C is equal to 2 times A to accommodate this boundary condition. And C2 is equal to 1, C2 here. So we are left, instead of having too many parameters, we are left only with 5 parameters using two extended SIR functions, right? So let's see how this works. As I say, we always try to simplify parameters, because otherwise we don't want to feed elephants, or try to, even when we feed an elephant, we try to feed it it's because this is a very complicated system. So maybe you need 4 or 5 parameters, 3 parameters, will be ideal, but it's impossible to feed it with so few parameters. I think 5 to feed a whole population or moving here and there is quite remarkable anyway. So if we compare the D2 prime, which is the derivative of 2D functions, and the extended SER2 models, the reduced versions, with 4 parameters for the D2 function here, D2 prime function, and 5 parameters as I just mentioned for the extended SER model, extended SER2 models. We see, and generally the extended SER model makes a better has better chi-squares. 6.8 here. The United Kingdom goes nicely like this, but the D2 function has a more pronounced peak, say, and the extended SER2 model, it has a little bit more like a plateau kind of function, right? So this is the situation for different countries at that time when we were looking before what was happening in South Africa. South Africa was still evolving or going up at that time, but we could see before what was happening in the European countries and other countries in the northern hemisphere. As you can see, the results were quite okay. I mean, the USA is quite a difficult country to fit, because probably many countries in one, right? So, and then we got good predictions overall, even for the US, Spain, Italy, United Kingdom, France. This is a kind of a global plot showing how things happen. And we went a little bit farther, and we use our physics knowledge on Planck model of photons from statistical physics. Our typical function here. Oops, I'm gonna click without moving to the next one. And so we did some by basing our knowledge, basing on the D function, always on the D function, give us an indication of the Monte-Carlo parameters that we need to use. Making obviously these Monte-Carlo parameters, they must have some kind of a logic. It's a little bit of an art to do this, but they must have some kind of logic. So where the temperature, determines the average energy of the individuals, which is related to how much you move here and there within its range of interaction. They are the typical temperature and energy parameters that we see in the Planck equation. We can adapt it to our situation on COVID-19. And so we did simulations for several countries. We did one for Spain, for Sweden. For Sweden also, you see this extended thing. It was quite remarkable at that time to predict what was happening in Sweden. Sweden was at that point a country of a black country. All the Western media was against what Sweden was doing, living without lockdown. There was a situation there, but it didn't go too bad at the end with Sweden. So, and here is what happened in South Africa. South Africa, actually, we have very stable parameters that they could predict the trend of the pandemic quite nicely, even if different regions they do a little bit different. The pandemic seems to start in the Western Cape and spread through the other provinces. But basically, this was something, and we are writing a paper right now. We're going to submit a paper soon on our Monte-Carlo Planck simulations. And then we realized something also very interesting, that if we use a normalized function for the D function, by shifting the D function to by a time max of the peak, basically when the peak is, we move all the different D functions to the same place, the same inflection point right here, and we divide by the total number of deaths, as I say, A over C, Remember, this comes from the D function, the L'Hopital function. So then we have that all these D functions, they suggest a universal pattern for the pandemic trend, right? For the US, Spain, Italy, UK, France, Germany, even Iran. Everyone has if we put all these D functions together, they seem to behave quite universally. So this was a big thing, that the cumulative data show the universality of the COVID-19 pandemic. Although with the D prime model, again, these are less statistics here, and there's more fluctuations. You don't see the same pattern as probably you see here. It's more difficult to see that there's any universality from this from the daily rates. Again, because this depends on it depends on how many deaths per day you have. So you don't want to have too much good data, right? But at the same time, you need high statistics to make it to make a good prediction here, or make a good conclusion there. But the cumulative data, as I say, is much more powerful, and that's what we use in many cases. So let's go to the second wave. I don't know how long do I have here. I almost done, no? But okay, let me give me 5 minutes.
Yeah, 5 minutes is fine. Yeah, thank you.
5 minutes, okay. So okay, 5 minutes. In 5 minutes, let's do to the second wave. So so these are the typical prediction plots. You see that in South Africa, the 10th of January, the 12th of January, already the 10th of January and the 12th of January, the D model and the D2. These are the D prime and the D prime 2 model. They already predicted that there was a peak by the end of January, but the extended SIR model, the extended SIR model 2, wasn't very happy with the data at that time. But as you move to 20th of January, then the situation, the propagation, error propagation becomes better. The 25th of January, everything became very clear. Then the extended SIR model converged with the other two, and this is the situation that we see nowadays. This is the plot of today. Everything, all these models have converged very nicely, and we keep going down the pandemic trend. As I say at the beginning, this is the lowest point that we have reached so far for the second wave. And again, we also did our Monte-Carlo simulation. And very importantly, here, the only thing that we changed with respect to the Monte-Carlo simulation that we did for the first wave was just the death probability. It seems like the new COVID variant has a different death probability, but the rest of the parameters were unchanged, were exactly the same for the two Monte-Carlo simulations, right? So this is also a very interesting result. Again, as I say, we rely on the D model first, but basically in this case, we didn't have to change any parameters besides the death probability. So moreover, a very interesting point, which was made on the 6th of February, this death excess, which is never considered, but according to the MRC, to the South African Medical Research Council, there were like 138,000 excess deaths between May 20 and February 2021, right? But the excess death, as everyone knows, measure the total number of fatalities from natural causes compared with expected death rate in a normal year. And it is expected that the vast majority of these deaths are linked to COVID-19. And this was the number, 138,000. This is the number that we get from the D model and from the Monte-Carlo. Total number of deaths after first and second wave of about 63,000, which is much less. It's almost, but almost the half of the excess death. So you may ask the question whether our calculations are reliable or not. Whether these model predictions are reliable if you don't have all the data coming in. These are we have 48,000, as I mentioned at the beginning, the first slide. These are official numbers of deaths from COVID-19 from hospitals, right? But we have 140 almost which are the excess deaths, and here we have what we predict. So 63 total versus 140. Some big car is at the back of my garage here. I hope it's not mine. So excess deaths are more than double. And then this is the key point I wanted to make. So this is the excess death. And besides the issue that we have a larger magnitude of more deaths here than we predict with the death model and with the extended CERN model, we see that the pattern is very similar. So despite the fact that we have more excess death than COVID-19 official death, even without knowing the total number of deaths from COVID-19, we can still predict. There's still enough representative data to predict the pandemic evolution trends. So as you can see, this is South Africa. This is the excess death. They look exactly the same. Not only that, also for the Western Cape, we also have a very similar pattern. You know, first wave, second wave. And this is the two functions of the D2 function, right? So again, the Western Cape, we also see that we are dropping very fast, going down very fast. But this will remain until probably next week. And when we start seeing, actually this week, when we start seeing some deviations probably here. But I mean, ideally, we would like to see this coming down, but probably some effects from a school will happen, and this will never be such a nice curve as we see here. And then last point, this is also very important because this allows us to predict the third wave. If you can bear with me for 2 minutes. So this was the Western Cape versus South Africa as a whole. So as you can see, the Western Cape started before the first wave, started earlier than the rest of South Africa, right? The rest of the provinces. Even for the second wave, here is the Western Cape, and as you can see, there's like a 10 days delay between the Western Cape and the rest of South Africa. So there are different arguments I could make. So like isolation of large population density, major ports, touristic attraction, Cape Town. You know, we can look at plots from other places which are quite isolated, and you can see that the situation of COVID-19 is very Uruguay, South Korea, New Zealand, Mongolia, all these very little casualties there. We can say that we have the issue with the townships where the spread happened at the beginning. And actually, this is a very interesting plot, very interesting, actually. The Western Cape government shows this interactive chart where we can go, well, basically, this was the first wave where Kailicha was on the top, and Tagerberg is always on the top because it's the main public hospital and the area. So Kailicha and Clifffontaine, they were the main townships along the N2. But then this has shifted in the last wave. And now there are other regions which play a bigger role in the pandemic cases. But I have no time for that. I will just mention one final thing. Another possibility is the burden of the disease in South Africa, where you have non-communicable diseases, diabetes, cancer, heart disease, strokes, which happen mostly in this area, the area of Gauteng. This we know from WHO that who is at most risk are those with diabetes, with heart problems, high blood pressure. So this is another situation why things may happen here in the Western Cape before they happen in the rest of the country. But the interesting point, if this is true, if we assume that this is the case, that it happened before, that there's always a beginning happening in the Western Cape, then if we assume that there's a slight delay, then we can see how the wave starts having an increased death rate. This is the Western Cape over South Africa death ratio. So as you can see, the death in the Western Cape increased to reach 80% of the total death pool in South Africa. And after some time, it comes down. And then there's a minimum here, which happened on the 27th of November. And again, the Western Cape started picking up on death with respect to the rest of the country. And this corresponds actually to the second wave, when this data is telling us that as soon as the Western Cape, if we assume again that things are starting before in the Western Cape with respect to the rest of the provinces, we must be looking at the Western Cape to South Africa death ratio. And if this number start increasing again, if this number start increasing again, there's a strong indication that there's a third wave coming. So far, this is the data as we saw it yesterday. So far, there's no indication for a third wave. It may well come because people are not wearing masks. I was the other weekend somewhere, and it was few people wearing masks and keeping distances. So the situation may happen, but so far there's no data indication. The data doesn't indicate that there's a third wave coming. But this is a perfect, actually, indicator, can be, and it can tell you, much earlier than the wave actually started a little bit later for everyone to realize that this is a very, very, here is the sensitive ratio. This is the UWC versus over South African ratio. You keep increasing this column here. You keep increasing, and then at some point it starts decaying. Once you reach the decaying up to the point of the 27th of November. From the 27th of November, the ratio starts picking up. 3 decimal points, very sensitive ratio, but start picking up to 0.225. This picking up of Western Cape versus the rest of the provinces was a clear indicator that a second wave was coming. So I can talk about the collaboration that we have, but we'll leave it for another time. Obviously, our main goal is to apply this. As I say, we are going to transform this grim subject onto something which can be used for students, where they can learn computational skills, mathematics, biology, physics. This is the application I was talking at the beginning, where you can change the range of the interaction, your mobility, your recovery time, as I mentioned before. All this probability of death, this is the probability that changed to reproduce the South African trend. You can get this application at this webpage, and you can play to see whether you can stop the virus, right? As I say, this is a unique opportunity for transformation. If we don't do transformation, maybe another wave, another pandemic will come and may hit everyone in a very bad way. So we need to do transformation now or never, I would say. It's the right time to do so. We have been doing it, but we should increase any effort on transformation. And then just a little bit of a positive side of the story. And we know Isaac Newton, he also have his plague, his bubonic plague, and he did his years of wonders at that time. And he the Principia, and I just wanted to have a little bit of a cartoon. I like to do cartoons from time to time, and showing Isaac Newton on his apple tree, everyone wearing masks, indicating that even the bubonic plague only lasted 2 years. Hopefully COVID-19 also lasts almost 2 years, no more than that. So, but for this, we need to keep safe, wear masks, wash hands, keep distance, and we are almost there. Thank you very much for listening. It was a little bit long, but I hope you enjoyed.
Thank you very much, Nico, for the very nice talk and the introduction to these very powerful methods that you use. And on another historical note, today is also the birthday of Galileo Galilei. Yeah, in I think it was 1642 or 1643. I don't remember, something like that. But it's today, so it's a very important day, and we should celebrate this evening a little bit his birthday. Yeah. Okay. Are there any questions for Nico, Ilya? And sorry, I invited Martin, Professor Bucher, to join us on the panel just to advertise his course that will start tomorrow morning at the NITheP Summer School. Yeah, And he will also speak of a COVID-related topic, but more on the genomic side of things. Yeah? And Nico already did his advert for March, where he will organize the traditional monthly NITheP summer mini school on exactly the model that he described, but probably at a more introductory level. Ilya, sorry.
Okay, yeah. So we've got a couple of questions. So there was a couple of questions on the way which were answered. I think that one question is also almost answered is, what can you say about a third wave? Do you think it will occur and when? Also, how bad it's likely to be?
So you see how bad it's likely to be. It depends on this virus, whether it change or not. As I said before, we had to change the recovery rate in our no, the death rate on our Monte-Carlo simulation here. So the death probability has to be changed because the COVID-19 virus changed. So be a little bit more, or actually double the number of deaths with respect to the previous wave, right? So this will depend on whether this virus change or not. If it doesn't change, our model predictions say that eventually we must recover, right? As time goes on and we have the same virus, we must get less damage. This is what the predictions say. And also whether we're going to have a third wave, everyone is talking about that, but so far there's no indication. Data, as I say here, as soon as things start picking up, there was some fluctuation at the beginning of the pandemic, but then it was clear that the Western Cape was increasing. So this was the beginning of the big wave, right? So then you reach a peak and then you start going down. So other provinces take over, and there's a migration of the pandemic evolution, right? The same thing happened here. On the 27th of November 2020, we already knew there were some indicators of having a second wave. So as soon as, it's very easy to plot this, as soon as this plot, as soon as the Western Cape, assuming again that the Western Cape is going to start the whole pandemic situation, these numbers start increasing, then we must be aware that there's a possibility. But so far, there's no indicators for a third wave.
Okay.
But it may come.
Thank you.
So far, sorry. Let me finish, because so far we don't have any indicators because we are still under level 3 conditions. Remember, the president said the new level 3 restriction, lifted the new level 3 restrictions, so people can go to the beach, the schools are opening now. So this is coming very soon, whether there's going to be any other effects. So far in going down here, this is all level 3 original level 3 restrictions. After 2 weeks, then we see what's happening. 2-3 weeks, we'll see what's happening here. So the next week or so, week or 10 days, is going to be crucial to see whether there's a third wave or not. But we know before the third wave actually almost started. You know, we're going to know if this is what I'm saying is true, which we have to check always to verify. But if what I'm saying is true, we can actually exactly pin down when the third wave will come.
Okay, and there is one more question, which is, what about lags in data? I mean, many countries, they share the cases of yesterday, for instance, in today's reports. The other question is about the robustness of these models, how they will do.
Okay, let me show you actually once I'm sharing this. So if we go here and we do, this is one of the codes that we're going to share with you guys, script. There's a little Python script here. Now we are collecting all the data from USA, Brazil, everywhere. So let me, for instance, give you an indication of, say, UK. So UK has been, right now has been, the data is coming from Worldometer. So that little Python script that we just we wrote, it brings us the data from Worldometer and update. In 1 second, we get the data updated to the 14th of February 2021, right? The same thing we can do with any country, you know. We can do with Italy. Let's see what happened in Italy. That Francesco is here. So 14th of February. Right now, we updated the data to see what's happening on the 14th of February, right? So we can do it. You know, this is coming down. Again, we see like another indication, and this may happen to South Africa at any point. Once the level 3 restrictions are lifted, this point here, this new bump, it may happen at any point. And this is probably what will happen. In our case, unfortunately, we won't be able to go down so easily. But let's go to Sweden, for instance. Sweden, right? So 14th of February also, we are going down. But there's a little change here happening. So you can see in all these countries, this is just real time. Switzerland, or you want Switzerland? Who wants Switzerland? Or Western Cape? You know, anything. Let's see Switzerland. You see Switzerland, for those who wants to go to CERN, the extended CERN model is just giving us a good indication. This one is not doing very well, but maybe is the fitting. Everything has to be fitted in the right way. So you see the dates of fitting is different or whatever. So there's always some discrepancies, but you need to fit things properly. I cannot just do with one fitting with one fit all the countries, right? I need to change the dates of fitting. I mean since when you are fitting. So so that's very robust because it's just predicting, as we mentioned before. There's a universality. There's also cases where things don't work out very well, and this is normally, as you can see here. I mean, we're not going to sell the motorbike here. So there are many cases where the situation is very difficult to comprehend. Like, for instance, all these cases here, right? So Russia doesn't look too bad at that time, but look at the USA, that was very difficult to predict this kind of behavior. In Peru, you know, this kind of up and downs. Ecuador, it was okay. Here in Iran, there was suddenly a huge wave coming, which was also very difficult to. So basically, you need to fit different waves separately. Here in Iran, everything was very nice until boom, we had the second wave, which was much bigger. So there are discrepancies between the models and the data, but this is either because there's a new wave coming in, but for a particular wave with similar conditions, initial conditions, the model works very, very well.
Thank you, Nico.
Okay.
Thank you. Just worried a little bit about the time. So maybe if there is one very urgent question, please raise your hand, or yeah, and we can give you
Francesco, we can do the seminars like they used to do it in Russia. Seminar until midnight seminars, you know.
Yeah.
forget about this 1 hour 45 minutes American seminars, you know. Let's do it like in the Russians used to do it. Let's do it until midnight, until we just fall down, everyone here, you know.
Okay,
but this is usually also done in person, so it's boring to do it online.
Yeah, that's true. That's true.
At least we have
and with a little bit of vodka, probably, no, Ilya?
Yeah.
Do we need a little bit of vodka as well to warm us up?
I'm afraid not a little bit.
I love those seminars, you know.
I guess before this degenerates a little bit, it's probably the right moment to stop the webinar for this evening, and maybe you can continue the discussion and organize a special workshop in private. Yeah? Okay, Nico, thank you very much for being with us this evening. It was really very interesting, and I think this was the best advert for your mini school in a couple of weeks. And yeah, thank you to Ilya, and thank you, Martin, so we managed to advertise your course starting tomorrow as well. Thank you very much for being here with us this evening as well. And thank you to all the participants. And as usual, we will upload the video on YouTube just now. Maybe we cut out the remarks on vodka, but
No, but these are also important remarks. You know, we need to.
I know.
To discuss until midnight is important, I think.
Yeah.
I think there's free speech with vodka.
Yeah, no, there is still free speech. That's true. Yeah. So, okay. So thank you very much. And please celebrate the birthday of Galileo this evening, because he really deserves it. Yeah.
Of course.
Thank you. Thank you very much.
Thank you so much.
Have a good evening. Thank you.
You
Thank
too.
you, Nico.